Good afternoon. Today I present to you PID Control Theory Lecture 1, an introduction. By the end of the lecture, you will know what is PID, why is PID needed, what are the applications, and the course contents. So firstly, before discussing what PID is, let's look at control theory as a whole. So control theory is about managing the system states to reach a desired goal state. So the first questions to have is, what's the system? And what is a state? So a system is anything we are interested in. A system could be a device like a car, anything. Could be car, plane, phone, anything you can think of. It's a system. Now what is a state? Well, a state is a variable of a system. A variable of a system. So for instance, speed could be one, distance, acceleration, location, temperature. So the car speed state could be 100 miles per hour. The system is the car, the state is the speed. A heater's temperature state could be 500 degrees. That is, the temperature is a state, the heater is a system. So control theory is about managing a system state to reach a desired goal state. So for example, if you wanted a heater, so desired goal is, say, for a heater to be 100 degrees Celsius. Well, different states of a heater could be the input power. And what a controller would do, would manage the input power so that it can get to 100 degrees Celsius. And that's the point of a controller. It takes an input and it tries to control the input so that it reaches a desired goal state. So one of the states being the input power, another state being the temperature. We want to manage the power so that we achieve a certain goal temperature, and that's what a controller is about. Simple basic example of a heater. So there are two categories of controllers in general, where the first one isn't even a controller, it's just a concept. Open loop control is the first one. Now what is open loop control? Well, let's take a simple heater for instance, and it is an output temperature. So a simple heater is just like saying, are you cold? Yes, then turn on the heater. So am I cold? That I'm saying as you as a person are asking the question, am I cold? Then turn it on manually. So you'll just click a switch and turn it on. Well, am I too hot? Then turn off manually. And that is what open loop control is about. It's all manual. It's like the heater can't detect if it's too hot or too cold. It's not able to control itself automatically. Everything is manual, so manual. And it has absolutely no perception of the real world. It's got no sensing. And typically cheap, so it's very, very cheap. Very easy to implement because you don't have to make a controller. And well, it's not very useful for a lot of things. I mean, for a simple heater it's okay, but something like a car or an aeroplane is not as good. Let's move on to closed loop control. A simple example being air conditioning. I'll draw a diagram and then we'll explain it. So closed loop control has three simple blocks, or three simple parts to it. Our first part being a controller, our controller. Our next part being our process. Our process for an air conditioning would be our heater or cooler. And so the process is anything we are trying to control. So it could be an engine process, or a rate of reaction, or a precision movement, and that would, or the motors for instance. The motors is the process. The cooler is the process. And then we also have this feedback part. Feedback / sensors. So how they connect together. Firstly, you will type something in a thermostat. So you'll say to the thermostat, I want the room to be 25 degrees Celsius. So that's called our reference. So reference is, we said we want 25 degrees Celsius outside. Now that goes into this little subtraction block here, which will calculate the error. We will look at this a little later. And this will go directly into the controller. The controller will do whatever it requires to the input power or the input states of the process so that it produces a desired output state, so a desired temperature. And then of course the process makes an output temperature. Now the output temperature of the heater is the output around the heater, around the heating module or around the cooler. Now the feedback sensors, they detect, are we actually at that temperature? Because you can heat up a heater to 50 degrees, but that doesn't mean your entire room is going to be 50 degrees. It has to slowly heat the room up. So the feedback sensors are this sensing environmental temperature, or ambient temperature. So the output temperature of the heater could now actually be maybe 35 degrees Celsius. But remember, you want a reference of 25 degrees. Now, of course, the feedback sensors are somewhere else and they're sensing the temperature of the room. And perhaps the temperature of the room is not at 25 degrees yet. It might be at, say, I don't know, maybe 18 degrees Celsius. Maybe someone opens a door and it becomes really cold all of a sudden. Whatever happens, the heater is 35 degrees. The heating module itself is 35 degrees. But the actual environmental, the room temperature is 18 degrees. And so this is the problem here. We asked for 25 degrees for our room temperature, but actually the room temperature is 18 degrees. And that's where this part here comes. We calculate an error. And the error is equal to the reference minus the actual temperature, or I should say current state or current temperature. And so our error here would be the reference 25 degrees Celsius minus the current state, which is current temperature state, which is actually 18 degrees Celsius. And so the error equals to, quick math, 7 degrees Celsius. So 7 degrees Celsius is over here. And so now we've said to the controller, well, actually, no, you want the environment to be plus 7 degrees. And so the controller will do anything to the process so that it can make up plus 7 degrees. Now say the new output temperature of the heating module becomes 40 degrees Celsius, because we now want to rise this temperature, so the heating module itself has to be higher. Now, that should be 40. Let's put that 40 degrees. Well, then now the feedback sensors are sensing the environment, and they find out actually you are at 28 degrees Celsius all of a sudden. I mean, obviously that should be a lot slower, but for an example here, so let's rub things out to make it neater. So if you're going to have to calculate a new error, remove the scribbles, pen. So the feedback sensors have calculated 28 degrees. So if you have 28 degrees for the actual environment, 25 degrees is still our reference. So our error is 25 degrees Celsius minus the current state, which is 28 degrees. And so that is minus 3 degrees Celsius. And so the controller will see minus 3 degrees Celsius. It will do whatever it requires to the input of the process so that it can get to that temperature. And then of course the output temperature might end up being now 37 degrees Celsius. And then now if you sense the environment again, and we find out it's now at 26 degrees Celsius. And you see this process keeps going on. It keeps trying to correct itself. It iterates constantly. So then what is PID exactly? So PID is just a type of controller. So that is our controller, and a type could be PID. There are many different types of controllers out there in the market, but PID being the main one. So PID is a type of controller, PID stands for proportional, that's an N, integral, differential. So PID, P stands for proportional, I stands for integral, D stands for differential. We'll look at what they mean in later lectures, but basically PID just uses three parameters, and the three parameters are proportional, integral, differential. So three parameters. P, I, and D. And so a PID controller is just controlled through these three parameters by tuning three parameters via controlling. Tuning the three parameters. So it creates our controlling action. So the entire PID controller is just based on three controllers. Based on three parameters only. So if we looked at what PID is, then why PID? Why bother using PID? If there are many different controllers in the market, why specifically should I use PID? Well, the main point of PID is, remember, if you have just tuned three variables, it's very simple to do. It's very simple to make or implement. And again, we are only tuning three parameters, so also computationally cheap. And what that means is requires very little processing power, so it runs on microcontrollers quite happily. Processing power. It also requires little memory, and because of that, you can run them on fairly tiny devices. Even smaller, low performance microcontrollers can sometimes run PID very well. Now, of course, that depends on the model of the system. So, if you're just trying to control, say, an air conditioning, it might be a lot simpler as compared to controlling the wing of an aeroplane or something. So, but generally, it is computationally cheap and it's very simple to implement. Another thing with PID is it's quite robust. Again, we only got to control three parameters, and controlling those three parameters does all our controlling for us. So it's because it's simple to implement, it's also quite robust too. It's also very safe because we can tune the PID parameters however you want to tune them. We can tune them in a way that is safer. So simple to implement, computationally cheap, robust, safe, and runs very quickly in real time. All controllers are real time, of course they have to be. But the main thing is, because it's so computationally cheap, it runs on real times on even very tiny microcontrollers. So let's look at applications. Applications are almost everywhere, motor control being one of them. So you might want to control the speed, so it may control the speed. Maybe control the position, so maybe if you want the motor to hold at a very certain angle. Typically used in automotive. So you may want to do engine control, cruise control. Another one being a robotic arm, or robots in general. So for a robot to hold a particular position, we need to use something like a closed loop control system, so that the robot constantly knows is it at the right angle. So robot arm control. And honestly, this list can go on forever, even satellite movement. It really just goes on forever. So now for the boring part of the lecture. What is the course content? So our first one is Lecture 1, Introduction to PID. We've just completed that today. Lecture 2, Understanding PID Parameters. We'll understand proportional, integral, and differential, and how they affect the controller. Lecture 3, Signal Characteristics and Transient Responses. This is about if you input a certain amount of power to a system, how does the output respond to it? Lecture 4, Tuning the different control parameters. And then Lecture 5, different types of PID controllers. You don't actually have to use all PID. You can just have a PI controller or a PD controller. Lecture 6, a Python simulation. We'll look at how tuning the different parameters affects the graphically, so you get to see what it actually looks like. Lecture 7, we'll do a C++ real-time control with ESP32 microcontroller. You can copy this code and use it for your own system too. Lecture 8, Advantages, Disadvantages, and more applications. And now for my favorite part of the lecture, which is the end. Thank you. Our next lecture will be Understanding PID Parameters. See you next time.